All right, so before we even jump into base conversions, there is a very simple assumption that I always like to teach my students when it comes to number bases. And there are some things that if we think about them, they apply to number bases no matter if we're counting with 1 or 1 million. And I'm not going to make you count with number base 1 million. We'll focus specifically in these courses on the bases decimal, which is going to be base 10, and we'll consider that our home base because that's what we most typically count in. We'll look at binary, which is base 2. We're going to look at octal, which is base 8. And we're going to look at hexadecimal, which is going to be base 16. But before we even jump into any of that, this is something I like to start with because it sets a really firm foundation for understanding how number bases work and why we write them out the way that we do. I'll draw just, about 4 different boxes or places here on the screen. And essentially what I'll do is I'll consider these placeholders for numbers. So you remember this from when you were younger. You would learn that, okay, you put ones in the one place, you put 10, and then you put 100, right? And you probably had some kind of workbook or you at least sketched this out on paper at some point. And this was really how you learned counting places and how these moved over. You probably had some kind of manipulative activity where you had, a couple of things and you had to count them out and put them in certain buckets or something like that. But either way, we fundamentally understand this in base 10 goes from 1 all the way up to, infinity, right? It sort of goes like ad infinitum. So if we take this idea and we kind of extrapolate it and look at does this apply and how does it apply to other numbers? You'll notice a pattern, and I'm going to help you with what that pattern is. If we take this, and don't check out on me here. I know a lot of people, when they see letters show up in math, they get a little bit panicky because maybe they've had a bad experience. I'm not asking you to do any kind of crazy math with these X's right here. But the pattern that you see with this, and that you'll see with binary, with octal, with hexadecimal, is going to be that this position of 1 is 1 because it's x to the 0 power. This will be x to the first power, x to the second, and x to the third. And like I said, this goes on ad infinitum. There we go, ad infinitum going this way. So if we come back over here and we just think for a second about how this all works out, x to the power of 0 is going to be 1. Any base to the power of 0 is going to be 1. And so this is our ones category. So in tens, we know that we write that out with the characters 0 through 9, right? And then when we get to 9, we roll this over and we go into the tens category. So we would put a 1 here and we do the same thing until we count it up to 9. And that's because this is x to the power of 1. So in base 10, to the power of 0, it's 1. To the power of 1, it's itself. 10 to the power of 1 is, 10, right? So this checks out. And then if we kept going, we'd see 10 to the power of 2, which is 10 times 10. Oh, well, that's 100, right? So our pattern's still holding up. And once we get to here, we see this would be 10 times 10, which would be 100, times 10. So we know 10 100s is 1,000. So our pattern is still very much holding up. And we just use zeros through 9s to write this out. So if I wanted to write out the number 999, well, that's 9 100s, 9 10s, and 9 1s, right? And so that's 999. So the reason that I like to teach this first is because this helps us set a foundation for what we'll do in other bases. So for example, if you took and we just sketch back out our same thing, but this time we kind of flip the script and we say not 10s, let's do 2s. And we take this base 2 and go through the same process. Well, we know 2 to the power of 0 is going to be 1. 2 to the power of 1 is going to be itself 2. 2 to the power of 2 is 2 times 2, which is 4. And 2 to the power of 3 is going to be 2 times 2, which is 4, times 2, which is 8. So this becomes kind of a go-to for me. That number one, it helped me memorize these. So now when I list these out, I know to go 1, 2, 4, 8, 16, 32, 64, and again, ad infinitum in this direction. It became a cheat sheet for me to where if I was in a CS competition, I'm grading a CS competition for students, if we're just working on something in class, this is a kind of home base that we can sketch out on paper and understand together that this is how every number base works, right? So in this, not only is it easy to sketch out on your paper, it makes it really easy to do conversions. And the reason that I wanted to start with this is because I want to show you in conversions, it's so easy to create essentially like your own math textbook. You can drum up problems at just the speed of thought, right? So if I come over here and I say, well, base 2, I want to know what the number 9 is in base 2, right? So 9 base 10, what does that equal in base 2? Well, right there, I have a problem, a conversion problem that I've drawn up myself, and it took next to no effort. So now what I can do with this is I can actually write this out. I can say, okay, 9, sure, I'll work from this direction, and I'll go this way, and essentially figure out how do I represent the number 9 base 10 in binary. Well, here's how you do that. You start with your 9, and you would say, okay, if I work this way, could an 8 fit in 9? Well, sure it could. So I put that there, and I represent 1. I would take 8 then away from there, and I'm left with 1. Would 4 fit into 1? Well, no, it won't. So I represent nothing in that category by putting a 0. Would 2 fit into 1? No. So I'm going to, again, represent this column with a 0. And then basically when I get down to this last 1, 1 will fit in 1. So I'll put something in that category. But then when subtracted, I get to 0, letting me know that I have finished writing this out. So you could go type this into Google, and you could check that 9 base 10 is the same thing as, if I wrote 1, 0, 0, 1 base 2. So a couple of things we want to recognize here. Any number base, no matter what we're talking about, is going to follow this pattern of going x to the power of 0 on to the x power whatever number as it just goes up, right? And that effectively, you'll see that just kind of exponentially double that number as it goes along. This pertains to every single base. And you'll notice when I wrote these out that I put the base right here because this would be confusing if we were in hexadecimal or something and I wrote out 9 and you go, well, is that base 10? Is that base 16? Also, you'll notice when I read this out that I didn't say 1001 base 2. I said 1001 base 2. 10 and 1,000 and those types of numbers are not numbers in base 2, right? Base 2 only has 1s and 0s. So this is effectively 1001 base 2. So now that we've kind of set these ground rules and we've got this basic understanding, we are ready to start jumping into some conversions. And in the next video, we'll tackle what it looks like to go from base 10 to other bases and back to base 10. I'm incredibly appreciative to you for watching this video. I make this content so that computer science education remains free and accessible. You make it all worth it. So please subscribe for more content and like the video if you learned something.